All right, here is the Unit 6 practice test. So starting with number 1, it says, for which of the following counts would a binomial probability model be reasonable? So A is a number of traffic tickets written by each police officer in a large city during 1 month. So the reason why that one doesn't work is because I guess we can say there are two options: success, failure. You write a traffic ticket or you don't write a traffic ticket. Independent, these aren't considered independent because the probability of someone getting a ticket is going to be different depending on what you're doing. So that violates the independent rule. The number of ones on a randomly selected set of 5 die. So looking at this one, in terms of two outcomes, success, failure, success would be getting a 1, a failure would be not getting a 1. So that works. It is independent. We're talking about rolling a die. There is a fixed number of trials, which in this case is going to be 5. And the probability of success is the same for every trial. The probability of getting a 1 in every case is 1/6. So it looks like B is going to be the correct option. If we look at C, this isn't considered independent because we're not drawing the cards with replacement. And D, for the same reason as A, the probability of receiving a phone call is not the same for every single phone call. All right, so starting with let's do number 2. So it says, let the random variable X represent the profit made on a randomly selected day by a certain store. Assume that X is normal with a mean of 360 and a standard deviation of 50. What is the probability that the store makes more than $420? So this is a z-score problem. So first thing we need to do is figure out what the z-score is. So z-score, we're going to do 420 minus 360 divided by 50. So going over to our calculator here. So it's going to be 420 minus 360 divided by 50. We get a z-score of 1.2. So in this case, we're trying to find the probability that z is greater than 1.2. So now we need to go to our z-score table. Okay, so looking at our z-score table, we see 1.2, that's 0.8849. 0.8849, but since we're looking for greater than, we need to do 1 minus that. So it's going to be 1 minus 0.8849. Which gives us 0.1151. So in context, I'm going to say the probability that the store makes more than $420 is 0.1151. All right, now looking at number 3, it says, referring to the information number 2, what is the probability that approximately 70% on a randomly selected day, the store will make less than how much? So less than we know is to the left, and this is a working backwards problem where we know that the area to the left is 70%. So we need to figure out what is the z for that particular percentage. So we're going to look at our z-score table, and we're going to find the closest thing to 0.70. So the closest thing to 0.70 looks like 0.6985, and the z-score is going to be 0.52. 0.52. So going back here, we know z is equal to 0.52. And from here, it's a working backwards z-score problem. So it's going to be 0.52 equals x minus the mean, which is 360, divided by the standard deviation, which is 50. So we need to multiply both sides by 50. So 0.52 times 50 is 26. So we have 26 is equal to x minus 360, and now we're going to add 360 to both sides. So this is going to be 386. So in context, I'm going to say the probability is approximately 7% on a randomly selected day. The store will make less than $386. All right, number 4. So this is an expected value problem. It says a business evaluates a proposed venture. It stands to make a profit of $10,000 with a probability of 3 over 20. So 10,000 with a probability of 3 out of 20 makes a profit of 5,000 with a profit of 9 over 20. It says break even, which means they make $0 with a profit of 1/4. And then lastly, lose 5,000 with a probability of 3 over 20. So to calculate the expected value, we have to multiply the profit times the probability and add them all together. So I'm going to put that in the calculator. All right, so when we put that in the calculator, we get 3,000. Oops. So the expected value for this particular venture is $3,000. All right, moving on to question number 5. So another expected value problem. It says a rock concert producer has scheduled an outdoor event. If it is warm that day, she expects to make a $2,000 profit. So if it's warm, we know that she makes a profit of $2,000 or $20,000. If it is cool that day, she expects to make a $5,000 profit. If it is very cold that day, she expects to make she expects to suffer a $12,000 loss, so negative 12,000. And it says, based upon historical records, the weather office has estimated chances of a warm day to be 0.60, cool day to be 0.25. So what we need to do is figure out what is the probability of a very cold day, assuming that those are the only options. Well, these two together is 0.85. We remember that the probabilities need to add to 1, which means this last probability has to be 0.15. All right, so now to calculate the expected value, we take the profit times the probability, and we're going to put that in the calculator. Okay, for the sake of making this video easy, when we put that in the calculator, you should get an expected value of $11,400. So the producer's expected profit is $11,400. All right, looking at number 6. So number 6, it says a basketball player makes 70% of her free throws if she takes 7 free throws in a game. If the shots are independent of each other, the probability that she makes 5 out of the 7 shots. So this is a binomial problem. And we're trying to find the probability that x equals 5. In this case, n, she's taking 7 shots. P, the probability of her making the shot is 0.7. And K, in this case, we're going to use is 5. So now we're going to go to our binomial calculator over here. We're going to type in our information. So probability of success on a single trial, that's going to be 0.7. The number of trials, she's taking 7 shots. And the number of successes we're interested in is 5. And we're going to look at this top row, so it's going to be 0.3176. And looking at our option choices, that's going to be 0.3188. So B is going to be the correct choice. All right, so same situation, 70% of her free throws, 7 free throws in the game. If the shots are independent, what's the probability she makes at most 1 shot? So again, binomial probability, at most 1 is less than or equal to 1. We have the same n and we have the same p. Okay, we're going to use 1, and we need to make sure we're looking at the less than or equal to symbol. So going back over here, we just need to change the number of successes in this case to be 1. And then we need to make sure we look at the correct one. Since it's at most 1, it's less than or equal to, so that's 0.0038. So in context, the probability that she makes at most one shot is 0.0038. All right, number 8 says in a triangle taste tester presented with 3 food samples, 2 of which are alike, and is asked to pick the odd one out by tasting. If the tester has no well-developed sense of taste, she can pick an odd one out only by chance, making a random guess. So the probability of that it's the odd one is 1 out of 3, since there's 3 different food samples. What is the probability that in 5 trials he will make 4 or more correct decisions? So we're trying to find the probability that x is greater than or equal to 4. That's 4 or more. N in this case is 5 trials. P we know is 1/3 or 0.33. K in this case, we're going to use 4. We need to make sure we're looking at the right one, greater than or equal to. Okay, so looking here, the probability of success, since we can only write it as a decimal, I'm going to write 0.333, kind of continuing. The number of trials, we're doing 5 trials. And we want 4 or more, so we're going to use 4 for K. And then looking at our answer choices, it's 4 or more greater than or equal to. It's going to be this case, so it's going to be 0.0452. So the closest one in that case is going to be option A. All right, number 9. So 17 people have been exposed to a particular disease. Each one independently has a 40% chance of contracting the disease. A hospital has the capacity to handle 10 cases. What is the probability that the hospital's capacity will be exceeded? So in this case, this is another binomial probability. Exceeded means more than what we can handle. So if we can handle 10 cases, we want to know what's the probability that it is exceeded, so more than 10. So N in this case is how many people have been exposed, and that's 17. P is the probability of contracting the disease, which is 0.4. K, we're going to use 10. Okay, so looking at our calculator here, the probability in this case is 0.40. The number of trials is 17. Those are the people exposed. And number of successes in this case is going to be 10. And we're looking for exceeded, which is a greater than symbol. So in that case, we're looking at this one here. So 0.035. So the correct answer is going to be B. All right, number 10, it says in a particular game, a fair die is tossed. If the number of spots showing is 2 or 4, you win $1. If the number of spots showing is odd, you win $3. And if the number of spots showing is 6, you win nothing. Let X be the amount you win on a single play of the game. What is the value of X? This is an expected value table. So I'm going to list out my outcomes. So the first one is showing a 2 or a 4. You win $1. So in this game, we're not paying to play, so we win $1. That's the profit. And we know the probability of that happening is going to be 2 out of 6, since 2 or 4 is 2 different outcomes in 6 die. Says if the number of spots showing is odd, you win $3. So odd would be 1, 3, or 5. So you win $3. And the probability of that happening is 3 out of 6. And then lastly, if the number of spots showing is 6, you win nothing, and the probability of that happening is 1/6. So to calculate the expected value, we take the profit times the probability. And then again, for the sake of time, I'm not going to put that in the calculator or show putting that in the calculator, but you should get an expected value of $1.83. Meaning if you play that game many times, you would win on average $1.83 per game. Number 11 says, referring to the game in number 10, what is your expected winnings for 5 plays? Well, if we know that our expected winning for 1 play is 183, we just have to take that and multiply that by 5. So if you do 183 times 5, you get $9.15. So the expected winnings for 5 plays would be $9.15. All right, next question, it says, our attitude toward shopping changes. We have a sample survey show that fewer people are doing shopping. We have a random sample of 2,500 adults if they agree or disagree that they like buying new clothes, but shopping is often frustrating and time consuming. So it says that 60% said agree if they're asked the same question. What is the probability that more than 1,520 in the sample agree? So this is a binomial problem. More than is a greater than symbol. In this case, we're looking at our sample size of 2,500. Our probability is going to be 0.60. And then we're going to use 1520 as our K value. So now going over to our table here, or our calculator here. So P is 0.60. The number of trials, that's our sample size. We looked at 2,500. And the number of successes we're interested in is 1520. And remember, we're looking for more than, which means we need to look here. So that's going to be 0.2014. So in context, the probability that more than 1,520 of the sample agree is 0.2014. 13 says, in the poll from number 12, what's the probability that less than 1,500 agree? So we're using the same N, the same P, but in this case for K, we're going to use 1,500. And we're looking for less than. So less than is going to be here, so that's going to be 0.4913. 0.4913. So the probability that less than 1,500 of the sample agree is 0.4913. All right, 14. This is another expected value problem. So in this case, to calculate the expected value, it's going to be 0 times 0.35 plus 1 times 0.20 plus 2 times 0.15 plus 3 times 0.15 plus 4 times 0.10 plus 5 times 0.05. So when we put that all in our calculator, should get an expected value of 1.6. So then it says if 3 tech support people are using telephones, what's the mean number? So we're going to take our expected value and multiply, 1.6, and we're going to multiply that by 3. So when we do 1.6 times 3, we get 4.8. All right, number 5, what are the 4 conditions required for a binomial setting? So I'm just going to say this verbally instead of writing it. So the first condition, that we can define a success and a failure. The next condition is that each trial or observation are considered independent. Condition number 3 is that there's a fixed number of trials or observations. And number 4, the probability of success is the same for each trial or observation. All right, now looking at this last one, so it says Billy's taking his midterm, which has 25 multiple choice questions, and he's not feeling confident at all. Billy knows he can get 5 questions right, and he knows he'll have to guess on the remaining questions. Each multiple choice question has 5 options. Billy needs 13 questions correct to pass his midterm. What's the probability that he passes his midterm? Okay, so this question's a little complicated. So we know that he needs 13 questions to pass. And we know that he can get 5 questions right. That means he's guessing on only 8 questions. Okay, and he needs basically to guess right on 8 or more questions. So we're trying to find the probability that x is greater than or equal to 8 questions. Okay, so in this case, we need to figure out what n is. Well, n is the number of questions he's guessing on. So sorry, he's not guessing on 8 questions. He needs to guess correctly on 8 questions. So there's 25 questions total. Okay, he knows 5 of them, which means that there's only 20 questions he's guessing on. So that's going to be n. Okay, for p, the probability that he guesses correct has to do with that there's 5 options here. So that means he has a 1 in 5 chance of guessing right if he's just guessing right out of the blue, which is also 0.2. So K in this case, since we know that he needs to get 8 out of the 20 questions right in order to pass the exam, we're going to use K is equal to 8. All right, so let's go over to our calculator here. So probability of guessing correct is 0.20. That's a 1 in 5 chance. The number of trials, he's guessing on 20 questions. And of those 20 questions, he needs to get 8 correct, or at least 8 correct. So in this case, at least 8 is greater than or equal to, so that's 0.0321. So in context, the probability that Billy passes his midterm is 0.0321.